Record the cloud. Okay, there we go. Do you have the packet, the key? So note, I'm going through this in-class review packet. So here's the link to that. It's go.osu.edu 1250 rev, meaning review. It's the same packet we worked through last week where these are just questions I made up in my head. There is no key to this packet because I made it up in my head. So the key is up here. So we're going to work through the key right now. Do you have the supplemental information for this exam? I posted the supplemental information on that resources page with all of the final exam materials, but you'll also find the supplemental information copied at the very end of the actual packet that we'll get to a little bit later. Basically, I give you everything, absolutely everything. I think really the only things you need to memorize are like polyatomic ion names, those charges, you know, those element names from the symbols. Like you need to know iron is Fe, all right? Like you need to know that. And Avogadro's number, I think, you should probably know that as well. But basically everything else I give you. There's just a small core of things that you should know. Also the seven strong acids probably is a flashcardable thing for you. Okay, so let's get started. And folks, for the 20 some of you on Zoom, make sure that you write to everybody in the chat box so we can all see what's going on in your mind. All right, so we left off in this in-class review packet on electrochemistry. We had already gone over some of the concepts of chemical equilibrium. So now we'll do electrochemistry. I've noted from a lot of you that electrochemistry seems to be a fun chapter that we like. Maybe I'll cut some more things out next semester and add a little bit more on to electrochemistry because of we were kind of rushed here at the end, though we did lose a class. All right, so electrochemistry is the last chapter on our final, and then we'll do some review for the rest of the packet. So, okay, electrochemistry. So let's look at this equation. I have a solid going into a plus cation and electron. What kind of half reaction is it? Not all at once. Oxidation, yes. It's an oxidation half reaction. There's a couple ways you can figure this out. You can use the Leo, the lion goes grr, Leo goes grr. So Leo is loss of electrons is oxidation. So you see that an electron is a product. So my thing is losing electrons, so it makes it oxidation. Or you can simply just look at the oxidation numbers of A. How is it changing? That oxidation number is going up. Its charge is going up. It's getting oxidized. And so an electron is lost in that process. So oxidation reactions occur at which electrode? Your anode. Yeah, so the other thing I guess to memorize is N-ox, red cat. So if I ask you, okay, in this balanced reaction, what reaction is occurring at the anode? Really, I'm asking you, what is the oxidation reaction? So just link those two kind of ideas together. It's not separate concepts you need to memorize. No, they just go together. Anode means oxidation. Versus we have this reaction, B2 plus goes to B. This, conversely, would be the reduction reaction. So Leo goes grr. Grr is a gain of electrons is reduction. So we see that B2 plus is gaining 2 electrons. Or simply, because I like numbers and I don't like memorizing things, I just see, okay, the charge of B is going down. It's getting reduced. It's going from +2 to 0, so it gains electrons to do that. And then this is the reaction that occurs at the cathode, okay? Reduction occurs at your cathode. Okay, so these are two half reactions. In order to build an electrochemical cell, you have to have both oxidation and reduction. I like to think, okay, in your oxidation reaction, you're generating electrons, and that feeds into your reduction reaction that requires electrons. So this is oxidation, here is reduction, and so that's why we say electrons travel from anode to cathode in an electrochemical cell, because you're generating electrons at your anode, and then you're consuming them in the reaction at your cathode. So these are the two half reactions. When we put together our electrochemical cell, I can give you reduction potentials for you to calculate the cell potential. So notice how, if we added these two reactions as is, would they perfectly cancel each other out? Would we get a perfectly balanced chemical reaction? No. Clearly, we have to manipulate this somehow. We have to double the oxidation reaction. I need to do the oxidation reaction twice for every reduction reaction I do once in order to make the two electrons cancel. So if we wanted to do, write the balanced redox reaction, we would do that. The balanced redox reaction would be, okay, I need two A solids, and I'll make two A pluses to generate two electrons, and then that feeds into the B2 plus reduction reaction to generate one B solid. So that would be the balanced redox reaction where I doubled the A reaction and canceled out the two electrons in the background. So N would be equal to 2 in this case. So even though I doubled the oxidation reaction, that doubling doesn't show up when we calculate cell potential. Cell potential is simply, the overall cell potential is simply the reduction potential that is at your cathode minus the reduction potential at your anode. Even though, yes, at the anode oxidation occurs, it's always cathode minus anode, both of them in the reduction form, because that minus sign does the flipping for you to turn this number into an oxidation number. So another way you could write this equation is you can say E cell is equal to the reduction potential at your cathode plus your oxidation potential at your anode, where these two equations, they're equivalent to one another, and that's because this term, your oxidation value is equal to the negative of your reduction value, all right? So these two equations are equivalent. I suggest just using this one. The reason is because you will always be given reduction potentials, always. You'll never go to a textbook and find like oxidation potentials unless it's like really specific for a specific reason. This way, as long as you know what the cathode and the anode are, you can just use the numbers as is from the table without doing any flipping. So simply in this question, if I tell you the reduction potential of A and B, and I know that A is my anode, B is my cathode, simply simply your cell potential, again, is cathode minus anode, both of them in the reduction form. So we use those numbers straight as is. It will be 1.0 volts minus 0.1 volts. So my cell potential is 0.9 volts. Notice how I didn't have to do any doubling. Yes, I know I doubled my anode reaction, but that does not show up in your cell potential. Where it shows up is in Gibbs free energy. So even if we had to, do some weird multiples with these half reactions, that manipulation does not show up at all in reduction values. It's just simply reduction potential at your cathode minus your anode, and that's it, all right? Okay. So there is the basics of electrochemical cells. So is this reaction spontaneous at standard conditions? It is, because our cell potential is positive, meaning that putting these things together at standard conditions produces a voltage that can then go do work, spin a little flag all day. Okay, so there we go. All right, so there's our standard cell potential. So if I set up this reaction and I force the A concentration right here to be 1 molarity, the B concentration to be 1 molarity, what cell potential should I measure? What is 1 molarity? What's the significance of that? That's standard conditions, all right? So this is not a trick question, but I'm assessing your understanding of what this value means. Okay, it's 0.9 volts, whatever. But when will we always read 0.9 volts if we put these two things together? No, it's dependent on the concentration, yeah. So the table values we use are measured at standard conditions, 1 atm of gases, 1 molarity of aqueous things. So what I'm trying to say is, oh, we're at standard conditions here. So if we're at standard conditions, that means we will measure a cell potential of 0.9 volts, all right? You can prove this to yourself by calculating Q. If you use the Nernst equation, All right, you can prove it to yourself that the Nernst equation always works, where the cell potential you'll actually measure is the cell potential at standard conditions minus some value over n log of Q. All right, so we already got E cell naught, that was 0.9. So what's kind of neat about standard conditions is when we're at standard conditions, when we do products over reactants, Q is equal to 1 because it's 1 molarity squared, I think. So I think Q here is equal to A concentration squared over B concentration. So if you do 1 squared over 1, you get that Q is equal to 1. And what is log of 1? 0. And so here we've proved it mathematically that at standard conditions, the book values that we get, cathode minus anode, is what we will measure, or very close to it, as long as the concentrations, Q is equal to 1, right? So then the follow-up question is here, well, what if we're not at standard conditions? Okay, so it's the same exact equation, but now, are we at standard conditions? No, we have a bunch of B and not a lot of A. So what will we measure this time? Now we use the Nernst equation. Q will be a number other than 1, but it's the same idea, all right? Take the concentrations that are actually given, calculate Q, and plug it into the Nernst equation. We already have E cell. We already got N was equal to 2. And then you just plug it in. So we'll see that our cell potential that we actually measure at these concentrations are just going to be a little bit different. So I'm going to go ahead and calculate Q. Q is, again, equal to products over reactants, just like any K expression. It's just we're not at equilibrium right now. So Q is equal to A plus concentration squared, note the 2, don't forget that, over your B, 2 plus concentration. Why don't I include the solids in there? They don't have concentrations. They never go into Ks or Qs, okay? Or liquids, just the things with concentrations or pressures if they're gases. Okay, so then plug in those concentrations that are actually given. So 0.5 squared over 2, that is equal to, I don't know, I don't have the key. So we gotta figure it out. So 0.5 squared over 2, and I get Q is 0.125. Okay, so it looks like I'm stacking this battery with more more reactants. See, the concentration of B is much higher than it is at standard conditions. So I think that this battery is going to pack a bigger punch than like the battery at standard conditions. But let's try it out, test it out for ourselves. What we will actually measure if we set up this cell with these concentrations equals the cell potential standard. So what we calculated before, 0.9 volts minus 0.0592 over N. So that was 2 log of that Q we just got, 0.125. All right, okay, log of that times 0.0592 divided by 2, 0.9 minus that. I get what we will actually measure is 0.93. Yay. Yay. So this is the Nernst equation. So this 0.0592 number just comes from putting all the constants together, putting the temperature together. But let me just take a moment to show you the actual Nernst equation. I think this would make although group projects are all submitted the make your own, I thought this would be a nice thing to explore. Do you ever hear like from your family or whatever, from adults saying, if your battery is dead or something, to put it in the freezer and it'll like give it more juice? You ever heard that like myth? Yeah, and so we explored that in office hours. And I was wondering too. And so we looked at the Nernst equation to see, hey, maybe, changing the temperature of your device will change the voltage. I don't know. And so we looked at the Nernst equation. So the Nernst equation with the 0.0592, that one lacks the temperature because I've already set it as 298. So let's just look at the Nernst equation at a different temperature. Let me find out where it is. Hold on. I have too many files. I think it's this one. Okay, so let's look at the Nernst equation. Or do I not give it to you? Poop, I don't give it to you. I give you the Nernst equation, but the one that's already set at 298. Let me just grab the other Nernst equation. Hold on. Because now I'm curious. Nernst equation. Okay, so the full Nernst equation is, crap. Do I not have it anywhere? All right. Okay, let's see if I can pull this out of my butt. All right. The cell potential is equal to the cell potential at standard conditions minus, I'm pretty sure it is RT-NF-ln-Q. I'm pretty sure that's what it is. That's the full Nernst equation. So we see, okay, where I just did, like, I put all the constants together, and that's where the 0.0592 comes from, and I convert the natural logs to logs because electrochemists like log scales, not natural log scales. But anyway, what you see here is that there is a temperature dependence of your measured cell potential at different temperatures. So let's think about this. So at like a low temperature, doesn't this term get really small? So your measured cell potential will be less, not as small as your measured cell, or as your cell potential at standard conditions versus at high temperatures. Let's do it at high temperatures, okay? At high temperatures, this term is really, really big. So what kind of cell potential will you measure? One that's a lot smaller. So yeah, putting it in the freezer should up your voltage than what it is at higher temperatures. But once you take the battery out and it warms back up, won't the voltage just go back to where it was? Yeah, so there is some truth into, I guess, putting your battery into the freezer to raise the voltage, but it's just gonna go right back to where it was once it reaches room temperature again. So there we go. All right, so if you've heard of that, I guess, wives' tale or whatever, you know, there is some truth to it. So it relates to these equations that we talk about. Okay, so neat. All right, let's keep going. Perfect. Standard conditions, okay. All right, so let's do some applications of the Nernst equation as well. This time, let's not calculate anything, okay? So the conceptual questions, again, just as important as the math-based ones because they're quicker. I hope that you can see trends. Here, I'm giving you the same equation. I'm saying let's start at standard conditions. So if we start at standard conditions, our cell, E cell, should measure 0.9 volts. But here's the thing, as this reaction goes forward, will we stay at standard conditions? We will not. We can start at 1 molarity, but once we start consuming stuff and producing stuff, those concentrations gonna change. So remember, a reaction is happening. So over time, as the cell runs, what changes? How does A concentration change? The A plus concentration. It increases, decreases, it increases because A plus is a product. This reaction is moving forward to generate electricity, while B concentration is going to decrease because it's a reactant, right? We can also talk about the masses of the anode and cathode themselves because the solids are a part of the reaction. They're not part of Q, but they're still part of the reaction. Oh, I have like a sneeze stuck in my nose. Let's see when it comes out. Okay, the A mass will do what? The mass of A will decrease because it's a reactant. B mass will increase. Oh, here it comes. Oh, no. Yes. Thank you. Thank you all. All right, so your A mass decreases, your B mass increases. Let's just look at that for a second. A, what did we define that as? Our anode. Right, so our anode loses mass, but our cathode gains mass, all right? So here's your anode. That is something you don't need to memorize. Don't memorize that your anode loses mass and your cathode gains mass. Instead, just think about how the reaction is happening. If you ever forget, just look at the reaction. And now let's put it all together and think, okay, we mentioned that the reaction starts at standard conditions, but it doesn't stay there. Right, so the value of Q, it starts as 1, but then it changes. It starts as 1 because we're at standard conditions. Q is equal to the concentration of A plus squared over B 2 plus. So based upon these answers, A increases, B decreases. This number gets bigger, this one gets smaller. The value of Q changes how? It goes up, yes. Or you can think Q is always products over reactants. As the reaction goes forward, you make more products. You make less reactants. So numerator gets bigger, denominator gets smaller. Where this is important is using that trend in the Nernst equation. E cell, can I rewrite the Nernst equation? I don't feel like rewriting it. Let's just bring you down here, because I'm lazy. All right. So as this battery runs, we say that, okay, Q gets bigger. So that means log of Q gets bigger, meaning this whole term, as this battery runs, gets bigger. So what happens to the measured cell potential of your battery as it runs for a long time? It gets smaller and smaller and smaller until that voltage is low enough that your device no longer works. Not necessarily 0 volts. Your battery isn't actually dead when it's 0 volts. It's dead much sooner because certain machinery or certain electronic devices require a minimum amount of voltage to get going. So once you're below that threshold, your battery is essentially dead to that device. And so that makes sense that your batteries, they just, they die over time because Q is getting bigger, your cell potential is progressively getting smaller. All right, so that's why things die. Okay, all right, okay. And then the last ideas here for review of chapters 12 and 13. What class is this? Engineering, okay. And that's thinking about batteries and electrolysis. So a primary versus a secondary battery. So batteries are galvanic cells. They're spontaneous cells. They're just more compact than our, zinc and copper solution sloshing around in beakers. They're just more compact. But we differentiated these two types of batteries, primary, secondary batteries. So a primary battery, is it a spontaneous cell? Is it a galvanic cell? It is, yes. We want to use a battery for its positive cell potential so we can harness its juice, A primary battery is not an electrolytic cell. An electrolytic cell is one where we supply electrons or electricity to drive a non-spontaneous reaction forward. That's what an electrolytic cell is. A galvanic cell is a reaction that's spontaneous on its own. An electrolytic cell is one where you supply electrons to force a non-spontaneous reaction forward, right? All right, what is the difference between a primary battery and a secondary battery? One's rechargeable. Which one's rechargeable? Secondary batteries, yes, they're rechargeable. If you think about, going from reactants to products, you go from A to B once and you can't go back to A for a primary battery. But a secondary battery, you go from A to B, you take advantage of its galvanic cell, its positive cell potential. But then when you recharge it, you go back to A. So actually a secondary battery is a galvanic cell in the forward direction. But how do you recharge a battery? You plug it into a wall. Right? So at that point, a secondary battery becomes an electrolytic cell in the reverse direction because you have to plug it into a wall to drive that non-spontaneous reaction backwards until you can use it again because that battery is rechargeable, right? Okay, so it's a galvanic cell, so it has a positive cell potential in this direction, but a negative cell potential in the opposite direction, but we take care of that by using electricity. That's a lightning bolt to mean electricity. Plug it in, make it go backwards until you can use it again, all right? But the big difference here is secondary batteries are rechargeable, primary batteries are not, right? I was just at Target. I can't go to Target without someone saying, hi, DrN. But I was just there and to buy a Monster because I gotta feed the beast. I'm the beast. I'm just real happy this semester's over. Though I do have to still grade all of your group projects. But basically everyone's gonna get a 10. Because you're all so creative. I read so many good ones. I'm like laughing and I wanna like share it with people, but like, I don't know if anyone would understand and appreciate it. So maybe next year, when I teach 1250, maybe I'll take a handful of your questions and make them group project assignments. I'll let you know if I choose you. Do you want to be chosen? Would that be cool? Yeah, that'd be cool. Okay, all right. I guess I should ask your permission before using, no, just use it. Yeah, all right. Okay. What was I saying? Oh yeah, batteries. At Target, at the checkout lane, they had 2 sets of batteries right there. One was rechargeable and one was not. The rechargeable ones was about double the price of the non-rechargeable ones for even just like half the number. I think the rechargeable ones only had 4 in a pack, but the alkaline batteries, the primary batteries, had 8 in a pack. And those 4 rechargeable batteries were about twice as much as the 8 of those primary batteries. And it's all about that reversible electrolytic, also galvanic chemistry behind those secondary batteries. Okay, so that's conceptual there. You know, the era of secondary batteries, you know, making that chemistry more environmentally friendly, more feasible, cheaper. That's basically kind of the cusp of technology of where we're at right now. You know, we have really great lithium-ion batteries, but safety is a concern. Mining is a concern. So you guys, you're the next generation to figure out that problem. How can we make it better? How can our phones get smaller and still last longer and not explode in our hands? That would all be great. Okay, so the last part of this chapter is putting it all together with the math. You all like math. And so really with these electrolysis questions where we electrolyze some ionic thing to make that neutral metal. We can do this by supplying the electrons. So we're reducing these cations into their elemental metals. So here I am delivering 150 amps. So here just memorize that an amp to chemists, it's more useful to represent it as a coulomb per second. So that means if I have 150 amps, what that means is I'm delivering 150 coulombs per 1 second. That's more useful to me, all right? We're also gonna use Faraday's constant, which rewritten as an equality is there is 96,485 coulombs in every 1 mole of electrons. I can't count electrons. They're like little ants all moving like in a row. There's just so many of them, I can't count them. But what I can measure is charge. So like mass or something. So coulombs is a measurable thing. Number of electrons is not. So what Faraday's constant is brings a relationship between the two. I can measure coulombs, therefore I can determine how many electrons were transferred during that event. So that is useful for us. And then the last thing is specific to what kind of compound is being electrolyzed. So here I am taking aluminum oxide and converting it into aluminum solid. So the easiest way to look at this is look at oxidation numbers and ask yourself how many electrons are required to do this process. So I see that 1 aluminum atom in aluminum oxide has what charge? So one of those aluminum atoms is +3 because the oxygen is -2. And there's 2 aluminums, there's 3 oxygens. So we are converting aluminum 3+ to aluminum solid. How many electrons does that require? 3, yes, there are 3 of them. So the last equality is 3 electrons, moles of electrons, is equal to 1 mole of aluminum. So essentially I just took the half reaction, aluminum 3+ plus 3 electrons gives us 1 aluminum solid, 3 electrons. I did get an email from a student about this. They were wondering, why is it 3 and not 6? Let me show you. So if you try to balance the half reaction fully, which we can do, you'll get the same answer. So here, Al2O3 goes to aluminum. So you can follow our 6 steps for balancing a half reaction. That works as well. All right. So if I wanted to balance this kind of more complicated half reaction, we'll still get the same answer. We start with aluminum oxide, we go to aluminum solid. So when we balance half reactions, we balance the atoms first, other than oxygen and hydrogen. So I need 2 aluminums to do that? Yes. Then you balance the oxygens using water, right? So if you do that, how many waters do you need? 3? 3 waters, okay? And then lastly, you balance the hydrogens using H+. So I think I need 6 H pluses here to make all of that charge balanced, or sorry, make all the atoms balanced. But now you need electrons to make it charge balanced. So notice that the only thing that has charge is those 6 electrons. So if you went through all that work and got, okay, 6 electrons are involved in this process. So a student emailed me saying, why isn't the number of electrons 6? It is 6, but how many aluminums did you reduce in this reaction? 2 of them. So the stoichiometry here is that 2 moles of aluminum requires 6 electrons. Aren't these the same? These are the same ratio, all right? So I just did it the lazy way using oxidation numbers. I know that this aluminum is 3+. To convert it to an aluminum takes 3 electrons. You can also balance the entire redox reaction and get the same exact answer. It's just this requires a lot more work, and I don't want to do it. All right, so I did email them back saying we are both right. We are both right, but in yours, you're just saying 2 moles requires 6 electrons, which is equivalent. Okay, so with all of these equalities, you can put it all together to figure out how many grams of aluminum we produce, and it's just fancy dimensional analysis. So in 5 hours, 1 hour is 360 or whatever seconds. After that many seconds, look at the equalities we have. So we're going to use the amperage here, where for every 1 second we deliver 150 coulombs. Once we're in coulombs, we'll use Faraday's constant. So we're in the unit of coulombs. I'll put that 96485 on the bottom. I'll put 1 mole of electrons up top. Then after moles of electrons, I'm going to use the stoichiometry from the redox reaction. 3 moles of electrons are required to reduce 1 mole of aluminum, and then to get it to mass, we use the molar mass. So 1 mole of aluminum is like 27 something. Nope, I rounded up, 26.98. That's basically 27. 26.98 grams, and so there we go. So how much aluminum do we make? 5 times 3, that, divided by 96485, divided by 3 times 27. We get 252 grams. Great, and that's how you make aluminum foil. All right, aluminum foil via electrolysis. Okay, all right, because you can't smelt it, all right? Aluminum solid doesn't just like fall out of a smelter like iron and copper does. That's why aluminum wasn't, I don't want to say invented, but really commercialized and industrialized until the 19th century. It's like it's one of the newer metals actually. Though now we just use aluminum to wrap our leftover food in. It was very hard to make until electrolysis came around. Okay, so that is all the new material. So we just did chapter 13. We did chapter 12 earlier last week in class. So what chapter do you want to go over? Okay, do you just want to go in order in this packet? Yeah, okay, all right. Like I said, I wrote the exam and then I wrote this packet. So I'm bunching chapters together. So we're not going to go through every single chapter. I'm just kind of like putting concepts together. Yes, in order, perfect. By exam. So I'm going to clump together chapters 1 and 2. In chapters 1 and 2, did we go too slow? Yeah, we did. Okay. Yeah? No? No. Okay. If you think yeah, did you take chemistry before? Okay. When did it stop? When was it finally new material? Chapter 13 was brand new? 12 and 13. Yeah, that's 1220 concepts, so yeah. Okay, I was just wondering. All right. All right, so chapters 1 and 2, so let's go through this fast. But here's the thing. Chapters 1 and 2, other than dimensional analysis, lots of concepts. So yeah, let's practice this. Okay, so is this sample is a what? Select all that apply. Is this picture a pure substance? So let's think about that, the type of pure substances we can have. Here's my trick. It's a pure substance if you can represent it with one formula and one formula only. Can you represent this sample with one formula? Yeah, what could it be? H2O. Is that one formula? Yes. So that is a pure substance. So there are two types of pure substances. There are compounds. I should do a different color. Compounds. Come on. Compounds or elements. Okay? So H2O is a what? Compound, yes. But a sample like helium or something, all right, and that would just look like a bunch of balls that were all identical, would also be a pure substance, but it's an element. So that's my trick. A pure substance is something that is represented with one symbol and one symbol only. Okay. Is this sample an element? No, because we just said it's a compound. Elements and compounds are both pure substances, but we differentiate them. All right, where a compound is composed of more than one element. More than one element. All right, so let me give you another example. Would N2 gas also be a pure substance? Yes, it would be, because it's one symbol. But is it an element or a compound? It's not a compound. Compounds are two elements. That's okay. It's actually an element, because nitrogen, it's just one element off of the periodic table. But here's the tricky part. Nitrogen is also a molecule. Molecule just means has bonds. That bond can be any atoms. It can be nitrogen, right? A nitrogen-nitrogen bond, that's a nitrogen molecule. Or it could be like CO, carbon monoxide. That's also a molecule, but that's a compound, right? So here's the thing, compounds and, how do I want to say this? I don't want to say this. All compounds are molecules, but not all elements are molecules. Because isn't nitrogen an element, but also helium is an element. Hydrogen is an element, H2, but only some of these are molecules, some of them are atoms, but both of them are elements. All of them are elements, all right? So that's a differentiation, all right. Does this contain a mixture? No, because a mixture is something with two or more pure substances, all right? So this would be like if I said, oh, you had a mixture of H2O and helium, all right? And I had like 2 helium atoms in there. So you need 2 formulas to represent what was in there. What if I said like NaCl aqueous? Is that a pure substance? That's a trick question. Because the phase aqueous implies what? Dissolved in water. So that means my sample contains both NaCl and water, so that's actually a mixture. Versus if I just said NaCl solid, yes, that is a pure substance. It's a solid, but when it's in the aqueous form, water is implied, so it becomes a mixture. So do keep that in mind. All right, so this sample is most likely, you already said it, water. Okay, water. Why can't it be CO? Not enough bonds or atoms, yeah. Well, can it be calcium chloride? That's the right ratio, 1 to 2, calcium chloride. Why can't it be calcium chloride? This is an ionic compound, so will it adopt this? What does this look like, the gas phase? Will ionic salts adopt the gas phase? No, so calcium chloride is ionic. Ionic things adopt crystalline structures, all right? It'll look like this with the right, atom, cation, anion ratio. So it's not gonna look like this. What about NO2? Will it look, is NO2 sample look like this? Yes, it will. Yeah, so this sample could be water or NO2. I don't know. Here, what I want you to locate is that this sample contains molecules, all right? Calcium chloride does not form molecules. It forms a extended crystalline network. But molecular compounds, which contain all nonmetals, make discrete molecules that bond to themselves and make these like discrete little particles. But calcium chloride, an ionic substance, even though it has the right ratio, we're not gonna see the discrete particles like this. Okay, when potassium and sulfur combine, what compound is formed? So we look at our periodic table and we see potassium is what kind of substance? Potassium is what element? What letter? Symbol? K, yes. Do you have to memorize that? Yes, you do. Yeah, you need to know that. Okay? And then sulfur is what element symbol? S, yes. I feel like at this point we've used them so much. I don't know. I don't know if I consider it memorization. All right, like knowing that carbon is C. All right, so we are combining these two substances. What kind of substance is most likely to be made? Ionic or molecular? Ionic, because potassium is a metal. And so here is where we predict charges. Ionic things are composed of ions, so we predict their charges. Potassium, most likely to make what charge? +1, because it's in group 1A. Sulfur, 2-, because it's in group 6A. Metals make cations. Non-metals make anions when composed of an ionic substance. So then we just combine it and it will adopt the structure, K2S, right? Where the charges tell us the ratio, but we are able to do that because this is a ionic compound. All right, so with that in mind, what will this sample look like? This one, let's just call this A, B, or C. What will this sample look like, A, B, or C? It is actually not A. This is an H2O solid sample. You look closely. Do you see the molecules, the discrete molecules? See how these are bonded to each other? These are bonded to each other, but here, there are just weak intermolecular forces keeping this sample together, all right? Ionic compounds, on the other hand, are made up of crystalline solids, where you have your anions and you have your cations, and they're spread around in that crystalline lattice to maximize attractions and minimize repulsion. So our sample is actually going to look like B, that crystalline network, all right? So ionic things look like this. Molecular things will make discrete molecules. I just made it extra hard here because I forced water to be in the solid phase, while in this example, water was in the gaseous phase. So it was kind of obvious that, you know, salt doesn't look like this, but you can clearly see a difference between these two structures, all right? And it's not gonna look like that. Here you have the right cation-anion ratio, but all of those ions aren't connected to at all. There are no attractions between those cations and anions. Okay, great. All right, how many of each subatomic particle are present in a tin sample? Okay, so tin, the number in the corner is called what? Is that the number of protons it has? It is not. It is the mass number, so it's actually the number of protons and the number of neutrons in that atom. So it's the sum, it's the mass number. So what I didn't tell you is the number of protons in this sample, but does that mean that you're lost? And nope, you can still answer it. You just have to look it up on the periodic table. So just let's be big girls and look it up. So tin has how many protons? 50, yes. Do you even have to know that it's tin? No, the SN, you just look for it on the periodic table, all right? You don't even have to know it's tin. unless I asked you what is the name, all right? And so there we go. So this subatomic particle has 50 protons. How many neutrons? 68, thank you. And then the number of electrons, so remember protons and electrons add up to the charge. So I see that this is tin 2+. It has, you can think 2 less electrons. You're not going to change the number of protons in the sample. You're only going to adjust the number of electrons. So there has to be 2 less electrons. So 48 will achieve that, where there's a negative 48 charge and a positive 50 charge, right? That's a low hanging fruit question. You grab them up quick, okay? Don't work on the ice table for 20 minutes and miss out on this question, all right? Okay. All right, so that was half of midterm 1. So the more meat and potatoes of chemistry is, molar masses, stoichiometry, all of that. So let's go through this, all right. Our periodic table, super handy. Yes, we have atomic numbers, but we also have molar masses. Molar masses, especially useful to us because they tell us how much each element weighs in grams per mole of that element. So mole is the counting number that chemists use to dictate a very, very large number of particles. And so the unit of molar mass from the periodic table is grams per mole. So if you look at carbon, carbon is 12.01 for its molar mass, which means 1 mole of carbon weighs 12.01 grams. So do recognize how to use that gram per mole molar mass. So we can rewrite the molar mass of this aluminum nitrate compound as 1 mole's worth of aluminum nitrate is equal to 230 grams of mass, right? That's really useful, right? So that's how we use dimensional analysis as well. Grams per mole, whatever unit is on the denominator gets an implied 1. And I saw this mistake a couple of times on the last group project. So molar mass is grams per mole, where it's 213 grams per every 1 mole. I saw a lot of 213 moles equals 1 gram. I saw it reversed sometimes, so do be careful and practice using molar masses often to ensure that the units cancel out correctly, so that's not right. Okay, so in here, how many oxygen atoms are present in a 5-gram sample of aluminum nitrate? So look at that oxygen in that compound. So let's make a relationship, just like saying 1 car has 4 tires. That's a relationship that we could use as a fraction depending on how we want to cancel our units. So let's say if I have 1 mole's worth of aluminum nitrate, how many oxygen atoms are there? 9. Yes, there's 9 moles of oxygen atoms. So if I figure out how many moles of aluminum nitrate I have, then I can figure out how many oxygen atoms I have and scale accordingly. So I'll start with the 5 grams given aluminum nitrate. So since I'm giving you a mass of aluminum nitrate, I want you to use the molar mass of aluminum nitrate. Don't try to use just the molar mass of oxygen. This is the mass of the full sample, not just oxygen. So where am I going to put the 213? On the top or the bottom? Bottom, yes. Grams, 1 mole of aluminum nitrate. Okay, next I'm going to use this conversion I got before. Where am I going to put the 9, on the top or the bottom? Top. 9 moles of oxygen go up top, and that's because 1 mole of the compound, AlNO3, 3 of them go on the bottom. Am I done? Nope, because the question asks for individual oxygen atoms. I'm in moles of oxygen, so what number do I need to use next? Avogadro's number. So 1 mole of anything, so in this case it's oxygen, is 6.022 times 10 to the 23 individual oxygen atoms. All right, and then there's that answer. You can do that. I don't know what the answer is, but that's the word for it. Okay, if we dissolve 50 grams of aluminum nitrate into half a liter or 500 milliliters of solution, what is the concentration of nitrate in molarity? So nitrate concentration in solution, all right? So molarity is the way we convey concentration of ions or solutes in solution. So nitrate concentration, molarity has the unit of moles per liter. Just like molar mass is like grams per mole, concentration is moles per liter of solution. So nitrate concentration of this solution is how many moles of nitrate I have present for every liter volume of solution I have. So if you look at the information given, I actually already have the denominator. I already know that this solution is half a liter. I already know that. But what I don't have is how many moles of nitrate that are present. But it looks like, just like we were doing before, converting aluminum nitrate to a mole amount using that molar mass. So let's take the 50 grams of aluminum nitrate, and I hope you see, oh, we need to convert that to moles, so let's use its molar mass. So 213 grams of aluminum nitrate is 1 mole of aluminum nitrate. Am I done? No, because the numerator in this molarity calculation requires moles of nitrate. If I stopped right now, I'm actually in the unit of moles of aluminum nitrate. So I need to take this answer and do what to it? Multiply by 3. Yes, for every 1 mole of aluminum nitrate, there are 3 moles of nitrate present, and then that's the number that goes in the numerator. So let's get that answer. 50 divided by 213 times 3. So there is 0.704 moles of nitrate present in half a liter. And so I think that's like 1.4 molarity or something like that. I think I can do that math right. All right, but the thing that elevates this question is I'm giving you a mass of aluminum nitrate, but I want you to tell me the concentration of nitrate. It's anion, where there's 3 anions for every 1 unit of that salt. So you need to make sure you multiply by that correct subscript that's there, depending on how that question is worded. All right, because if it was backwards, if I asked you, okay, you want to make a nitrate concentration of this, how much aluminum nitrate do you need? You would have to divide by 3 in that example. But it's just application of dimensional analysis. Okay, so that's midterm 1. So let's just skip, y'all, I feel like are good with gases, so I'll just skip that. Move on to electronic structure. So how light is related to how we discovered a lot of the intricacies of the electron on our atom, the electronic structure of our atom, that light interacts with matter based upon the energy levels of the electron. And so the energy gap is related to the wavelength of light that we're either observing or that is being absorbed or emitted from that atom. So light, the equations for light, that is given on your supplemental information. But if I remember them correctly, we have the equations of light as the speed of light is related to its wavelength times its frequency. But that equation isn't as useful. I feel like the one we use all the time is energy is equal to Planck's constant times its frequency, or energy of your photon is equal to Planck's constant speed of light over wavelength. So I feel like these 3 are really useful to us because it makes the relationship between energy, wavelength, and frequency. High energy photons have short wavelengths and large frequencies. Low energy photons have long wavelengths, okay? So like radio waves, microwaves have much longer wavelengths than like UV light or X-rays, but they have small frequencies. So with that in mind, arrange these from highest to lowest energy. All right, so this is parts of the electromagnetic spectrum. So which one has the highest energy here? X-rays, very good. And then next up, UV, then it's going to be blue light, then it's going to be red light, then it's going to be infrared light, has the lowest energy, right? Infrared light just feels warm to us, okay? Red light and infrared light, they're very related to one another. That's why it's called red light and infrared. While UV light, UV stands for ultraviolet, so UV is closer to the higher energy realm of the violet, purple, or blues of our visible spectrum. And then blue light, also part of our electromagnetic spectrum. So here I talk about energy, right? But I could simply rearrange this question to, instead of talking about energy, I could say, how could I change this question to be about wavelength? All right, how could I change this question so the answers stay the same? So high, low energy, at the top, we're looking for what kind of wavelengths? Short, yes, short. And then long wavelengths is low energy, or I could talk about frequency. This would be large frequencies, small frequencies, all right? So same idea. Okay, great. All right, okay, what kind of orbital is the highest energy electron on an aluminum atom? So, you know, we've looked at electron configurations of atoms based upon where they are on the periodic table. The periodicity of properties that we see for elements is based upon those electron configurations and the energies to gain or lose electrons. So here I'm just assessing that, but do you understand like what is the highest energy electron and to assign quantum numbers for it? So the strategy here is to write out the electron configuration for aluminum. The highest energy electron is going to be the electron in its valence shell, right? In its valence shell. Basically, it's the last electron you place when you write out the electron configuration. So let's go ahead and do that. We'll just use shorthand here. So shorthand allows you to use a noble gas as like a checkpoint to take care of the first 10 electrons for us, where aluminum just has 3 extra electrons that we need to place. But we start with an neon core. So after neon comes sodium. Sodium is in what orbital? An S, but which one? 3s, yeah, so if you forget, just remember hydrogen starts at 1s, so it's 1s, lithium's 2s, sodium's 3s. Then we move over to aluminum. What block is that? P, but which one? 3p, yes. Oh, wait, sorry, 3s, how many s electrons can we place? 2, yeah, so we move over 2, and then it's 3p, and then how many electrons do we place? 1. Very good. So here, aluminum is 3s2, 3p1. So which do you think is the highest energy electron? That 3p, yep, is the highest energy electron. Or let me ask you this way. If you were to remove an electron from aluminum, what electron would you remove? Would you remove a 3s or a 3p? You're going to remove that 3p because look, if you write out the electron diagram, okay, if we were a predator and we were wanting to take an electron, which one are we going to take? The one that's all alone, because it takes the least amount of energy to take that lonely electron versus the 2s electrons where they're paired, so it's more stable. It's going to be harder to remove. So this energy is the highest energy electron because it's easier to remove. So that's the answer. So 3p, I guess, is the answer. Okay. What are the quantum numbers? So it's the last electron, essentially, that you place. What are the quantum numbers for that electron? So our quantum numbers are n, l, m sub l, and m sub s. So n is equal to what for that electron? 3. Yeah, so this is n, that is l. So l is what? 1. But I thought L could be 0, 1, or 2. That's true. That's true. But this, I'm talking about a specific orbital here. I'm already telling you that this is a 3p orbital. So we can, yes, say that L is equal to 1 in this case because it is a p orbital. All right. When I say that, like, depending on your n, L is equal to 0, and all the integers up to n minus 1, those are the possible L's that you can have, the accessible orbitals that you have. But here we're dictating, saying that this is a p orbital. All right, here is where things get a little bit tricky, because notice when I drew the electron diagram, did I have to put that electron right here in the leftmost box? No, I didn't have to. Could I have put it here and it's the same energy? Yes. What about here? Yes. What if I flipped that sucker? That's okay too. It's just for some reason we like to put electrons in left to right and starting spin up. I don't know why. It's just we do it because as humans we read left to right. So all of those are the same energy. So what that means is once we get to M sub L, we have some options. That M sub L can actually be equal to -1, 0, or +1, any one of these boxes. M sub L are basically the boxes that are in here. I'm saying you can put an electron in any one of those boxes and they're all gonna have the same energy. It's just for some reason we always like to put them in the leftmost one, right? And then same thing for spin. Do I have to put that first electron spin up? No. Do I have to make it spin down? No. So it could be +1/2 or -1/2. It doesn't matter, all right? So all of these combinations are valid quantum numbers for that highest energy electron on aluminum. N has to be 3, L has to be 1 because of, we said it was a 3p orbital, but the rest of the numbers can be optional just because there's multiple boxes we can put it in. Okay, more fun. All right, of each pair, what is the larger particle? So when thinking about size and periodic trends, these are the things you look for. You look at the N value. As we go down, more shells, atoms get bigger, okay? That's the first thing you look for. The second thing you look for, if two things are in the same N, you look for Z effective, where elements on the left, like potassium and calcium, they have low Z effectives, low effective nuclear charges. So are those electrons really attracted to that nucleus? No, an electron is not super attracted to a +1 charge. But how about like neon? Neon has what effective nuclear charge in its valence shell? +8. If you were a dumb little electron, are you more attracted to +8 or +1? +8. So neon, a lot smaller. So here we see, and this is weird, that elements actually get smaller going left to right across the periodic table. And what we see is that size basically explains all of the rest of the trends as well, right? It's harder to remove electrons from atoms that are small. You get more energy back if you put an electron on something that's already small. All right, so which one's larger, aluminum or nitrogen? So I usually just look at the N value right straight up. So aluminum is N equals 3, and nitrogen is N equals 2. So which one's bigger? Aluminum, okay. Aluminum or silicon? So here, both of them are N equals 3. So what are we gonna look at instead? Z effective, aluminum. Z effective for valence shell electrons is just its group number. So the valence electrons on aluminum feel a charge of +3, but silicon, they feel a charge of +4. So in which case are those valence electrons, I guess, less attracted, I guess. So it would be aluminum here, aluminum. That those valence electrons are less attracted to a +3, resulting in a larger atom. All right, aluminum or aluminum plus? Aluminum is bigger. So here with ions, cations are always smaller. Anions are always bigger. And it's because cations have less electrons, anions have more electrons. And then there's some special cases with isoelectronic things. Isoelectronic things are particles with the same number of electrons but different number of protons in the center. So you just compare number of protons there. All right. Okay, so aluminum normal is bigger because aluminum cation is always smaller. So then which one is bigger in the last one? Aluminum regular or anion? Anion. Bigger. Okay. So we got the particles, so same exact list. Which one has the larger ionization energy? Meaning, in which case is it harder to remove an electron? When is it going to be harder to remove an electron? When the atom is big or when it's small? When it's small. So really, what is this question asking? Which one is smaller? Yes, thank you. Which one's smaller? So between aluminum and nitrogen, nitrogen has the larger ionization energy because it's smaller. Silicon, because it's smaller. Aluminum plus, because it's smaller. Aluminum regular, because it's smaller. All right, last one. Which one has the more favorable electron affinity? So here you're thinking, okay, you're placing an electron back on to make the anion. In which case, is it more favorable to put that electron on? So in general, it's very favorable to put an electron on if your particle is small. So again, we are looking for which one is smaller. You'll get more energy back, more attraction, if that added electron gets close to that nucleus. So here, aluminum or nitrogen, nitrogen is more favorable to put an electron on, right? Nitrogen is a nonmetal, aluminum is a metal. Nitrogen typically will make a anion, but aluminum is a metal, typically makes cations. Aluminum or silicon, here, silicon, I think, yeah, is smaller, so it's going to be more favorable to put that electron on. Aluminum or aluminum cation, which one is it more favorable for this electron to stick onto? The cation, because it's smaller, yes. Also, it's already positively charged, right? There's a lot of attraction between, positive and negative charged things. And then the last one, aluminum or aluminum minus, just regular aluminum, because it is smaller, yeah. Also, does this electron feel attraction to that aluminum minus? No, that's repulsion. So that's not super favorable to put that electron on there. Okay, so that was chapter 6. Okay. Order these bonds from least to most polar without an electronegativity table. Do I ever give you an electronegativity table? No, I never do. But the trends are, all right, off of our periodic table. So let me just make a crude periodic table. Which element is the most electronegative? Fluorine. Fluorine is the most, right? Has the highest electronegativity, and the least? Cesium, metal, least electronegativity, all right? And then so we see electronegativity decreases going from fluorine to cesium. The last piece of information you need to know, so fluorine, yes, is the most electronegative, but I also like to show your attention to the high 5. And that is 5 elements that also have high electronegativities, and that includes fluorine, chlorine, and oxygen. And then, no, chlorine isn't there, hold on, I messed up. I forgot my elements. Fluorine, what comes next? Thank you, oxygen, and then nitrogen. That's my high 5 within that row. Then going down, it's fluorine, chlorine, and bromine. So all 5 of those elements, nitrogen, oxygen, fluorine, chlorine, bromine, all have very high electronegativities. All of them are above 3, where everything else is rather low, right? So if you stick one of those suckers on an element or on an atom, you typically get a polar bond, except for some cases, which we'll talk about. Okay, so here, let's rank these from least to most polar. Which one is obviously the least polar? This one, all right, that oxygen, oxygen, this has a difference in electronegativity of 0. It doesn't matter if you know what oxygen is or not, it's going to be 0, because when you take the difference of the same number, it's going to be 0. So this one's the most nonpolar. Now this is where things get tricky. Here we have oxygen either attached to a chlorine or or a carbon. All right, so this is kind of tricky, because if we look and see where carbon is on this periodic table, I'm looking at what is the electronegativity difference between carbon and oxygen, and I'm comparing it to oxygen to chlorine. So if you kind of look, it seems like they both are similar distances away from one another, but in one of these examples, it's you can determine without the table which one has a smaller electronegativity difference. And that one is going to be the chlorine-oxygen bond. And the reason is because chlorine and oxygen are both very electronegative. And so if you subtract two large numbers from one another, you're gonna get a small number out. So both of these, so like both are electronegative, are pretty highly electronegative. So delta En is going to be small. Versus carbon is, has a fairly low electronegativity, but oxygen, on the other hand, has a high electronegativity. So that means its difference is going to be larger. All right, so if we want to order this from least to greatest, CO is going to have the greatest electronegativity. So this one's going to be the most electronegative. Right? ClO, still electronegative, but not so much because both oxygen and chlorine have high electronegativities. Okay, great. Okay, so let's draw some stuff. Let's draw OCl2 and then predict its electron geometry, molecular geometry, and polarity. So here we have to do the 6 steps for Lewis structures. So that first step for drawing a Lewis structure is doing what? Counting valence electrons. So oxygen has 6. There are 2 chlorines, so 2 times 7. That is equal to what? 20? Okay, what do I do next? You draw the skeleton structure, so you put oxygen in the middle, and then you draw 2 chlorine bonds. So far I have drawn 4. Next, what do I do? Outside, then inside. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I fulfilled the octets of chlorine, and then the 4 extra electrons I had left over, I put on the oxygen atom. Okay. So what is the electron geometry? So to do electron geometry, you focus on the central atom and you count how many electron domains are there. There's 1 bond, 2 bond, 1 lone pair, a second lone pair. So this has 2 bonds, 2 lone pairs. So this adds up to an electron domain number of 4. So what is 4? Tetrahedral, yes. Okay, so if all 4 of those electron domains spread out evenly, they will make a tetrahedron, which looks like this in 3 dimensions. All right? Where each of those legs is either a bond or a lone pair. I'm not differentiating between them, right? That's if all of the, where electrons are made shape. But what we care about is also the molecular geometry. Molecular geometry only cares about where the bonds are, right? Does that mean that this molecule becomes linear once we talk about the molecular geometry? No, those lone pairs are still there. So what I like to do is just cover up the lone pairs that I've indicated. There are 2 lone pairs. So put 2 lone pairs on this tetrahedron and tell me what shape is left over. What would that be? Bent. Yeah, so you put 1 lone pair, then you put another lone pair, you cover them up, and you think to yourself, okay, what's left behind? Oh, you can't see that. What's left behind? That is a bent structure. So here, the geometry is going to be bent. What is the bond angle about going to be? Is it going to be 120 bent or 109 bent? 109.5. Is it going to be exactly 109.5? It is not. It's going to be slightly less because of those lone pairs screwing things up. All right, so it's bent. Is this molecule polar or nonpolar? Yes, it is polar. Yes, because it is bent. All right, because if you look at this, if you look at the Lewis structure that I drew, this don't look bent. This looks flat, or this looks linear. So it looks like this compound is nonpolar. But remember, Lewis structures do not communicate molecular shape. You actually have to apply Vesper theory yourself. Yeah. Sometimes, yes. So here, let me give you, and I like that you gave that example because here oxygen is a tetrahedral, the electron geometry, and carbon, when it has 4 bonds, is also tetrahedron. So let me give you an analogy. All right, so note that this oxygen has how many electron domains? 4. But let's draw methane. How many electron domains are on that carbon? 4. And its molecular geometry? Also 4 tetrahedral. There are no lone pairs. Is this molecule polar or nonpolar? This one's nonpolar because it's a tetrahedron, but are there any lone pairs you have to put on? No, they're all identical, all right? But here's where things get messy, okay? Once I have carbon, all right, once I have carbon, what if I have 2 things that are different? What if it's like this? It's still a tetrahedron. It's still 4 electron domains, but it's different now. And actually, I hope you can draw analogies to this. Look, where should I put this? Okay, just delete you, put you here, all right? Draw analogies here. So we have this oxygen with 2 lone pairs, 2 chlorines. Look at this carbon. It has 2 hydrogens, 2 fluorines. It's really no different. The carbon atom looks like this. There's 2 fluorines here, 2 hydrogens over here. This would also be a polar molecule because we have 2 types of bonds that aren't identical. They don't have identical electronegativity differences, so their bond dipoles do not cancel out in 3 dimensions. I don't care that you actually add up the vectors, you just need to know that they don't cancel out in 3 dimensions like you see here. These fluorines are pulling on the molecule differently than these 2 hydrogens. So I like to think that like this kind of geometry and thinking of polarity is really no different than this molecule. Also, this molecule is analogous to what common molecule that we interact with every day? Water. Yes, it is analogous to water where we have oxygen, but we have hydrogens and 2 lone pairs. So here, this carbon-containing molecule and then this, water-looking molecule, they have the same electron geometries, but different molecular geometries. But both are polar because of those either 2 lone pairs or 2 atoms that are different. Does that help? Okay, all right. All right, good. So that's the 6 steps and how to do that, because I can't have you draw on the exam, but I can ask you about polarity and geometry because that requires you draw it correctly. So count those electrons. All right. Okay, so OCl2 again is a gas at room temperature. Water is a liquid at room temperature. So what does that mean? Which one has more intermolecular forces present, OCl or water? Water is a liquid. All those particles, they're stuck together, versus OCl2 is a gas. So are those particles very much attracted to one another? Not so much. So which sample has more intermolecular forces in the sample? Water. Water. Okay? They're stronger in water because the room temperature, the same amount of kinetic energy present, water cannot overcome those intermolecular forces. That room temperature is not enough. So why is that? Why does water have more intermolecular forces? Is it because it's heavier? Is it because OCl2 is heavier? That can't be the reason. Because if OCl2, if that was the reason and it was heavier, then OCl2 would have more IMFs. It would have the higher boiling point temperature, but that's not what we see, okay? Or why? Is it because water is polar and can dipole-dipole? No, that can't be right because OCl2 also is also polar, and can also dipole-dipole. So if that was true, they would both have identical intermolecular forces, identical boiling point temperature. So the real reason here, and that's water is very special in our world, is that it can hydrogen bond, which is why the water is a very lightweight molecule, yet it's still a liquid at room temperature because of those strong hydrogen bonds. So that makes the difference here, that water, for being a light molecule, is a liquid, has more IMFs because of the presence of hydrogen bonding. Okay, are we almost done? Oh my gosh, yes. Okay, keep going. Okay, chapter 9, true or false, you are the system. Are you the system? Do you matter? No, false, yeah. You are not the system. You are the surroundings. So, if the cup gets hot, the reaction has what sign of delta H? Negative. If you feel heat, it's because the reaction lost heat. Okay, so your feelings don't matter. It's all in reference to the reaction. If you get colder, it's because the reaction took heat from you and it gained it. So it has a positive delta H, all right? Okay, yeah, if a reaction occurs in water and the reaction has a positive delta H, do you get hot or cold if delta H is positive? You get cold, yeah, so the water temperature goes down. That's weird. And 50% of you will still make that mistake. Okay, so if delta H of the reaction is negative, the reaction loses energy, loses it, okay? So as the surroundings, what do we observe? We see the water change its temperature. How? It gets hotter. Yes, it gets hotter. If the reaction loses energy, it's going to shoot it out into the world, into the universe, into us. So we feel it get hotter when the reaction loses energy, okay? You will still mess up. And this is why when we talk about the first law of thermodynamics, it's always Q lost, negative Q lost somewhere is always gained somewhere else. We have to put that negative sign there. Because the whole idea of the first law of thermodynamics says that the energy change of the universe stays constant, or it stays constant, so it's zero. So the idea if we move these things around, 0 equals Q gained minus Q lost. And so this would equal 0 if those two values are the same. That's how we get 0. And that's why that negative sign is there. Wait, did I do that right? No, I guess there. Yes, Q gained is Q lost, where one of them is negative. So something is gaining temperature, something's losing energy versus in temperature, and so the energy of the universe stays constant there. Okay, so that's enthalpy. So make sure you get those signs right. Okay, entropy, different. This is delta S, entropy. So not necessarily, measure of disorder, but that'll still get you the answer right 50% of the time. Really, entropy is the measure of microstates. But entropy is useful for us because this is the second law of thermodynamics, predicting the spontaneity of a reaction. So there's two ways we looked at spontaneity in chapter 10. So reactions are spontaneous if delta S of the universe is what sign? Positive, right? That is the second law of thermodynamics. All spontaneous processes have positive changes of entropy of the universe, where the universe, all right, delta S of the universe is equal to the delta S of your system plus the delta S of your surroundings, right? So of everything, right? So that's neat because, we thrive on spontaneous reactions in our life, batteries, whatever. So if all spontaneous reactions are increasing the entropy of the universe, isn't the entropy of the universe always increasing? Always, always, always? If everything is spontaneous, yeah. And that's the whole premise behind the heat death of the universe, right? If you've ever gone down that rabbit hole of looking into that kind of philosophical aspect of thermodynamics and energy, is that with anything that we do that is spontaneous, we are constantly increasing the entropy of the universe so much that won't eventually it approach infinity. And if we have an infinite number of microstates, basically our world will just become unrecognizable. We'll have a maximum amount of entropy or a maximum amount of disorder where nothing is unique anymore. And that's like a philosophical kind of, I don't want to say like religious thing, but there's a lot of science folks who are really behind the heat death of the universe. So you can look that up if you want some light evening reading, all right? Okay, so that's where that comes from, the second law of thermodynamics, okay? But see, tracking the universe sucks. I don't like looking at everything in the world. So oftentimes we can just look at delta G of the reaction instead. So for spontaneous reactions, what kind of sign of delta G are we looking for? Negative, right? but they still describe the same thing. Any reaction with a negative delta G reaction is going to have a positive delta S of the universe. It just is hard to track the universe. Okay, so if we have a reaction that is at equilibrium, that means the forward reaction is not spontaneous. The reverse reaction is not spontaneous. So that means delta G is 0 when a reaction is at equilibrium. Neither the forward or reverse reaction is spontaneous. So if we have this reaction, solid to liquid, and I give you enthalpy values, enthalpy and entropy values, we can use this idea of, okay, solids, a solid sample is in equilibrium with its liquid phase when delta G is 0, delta G is equal to delta H minus T delta S. So let's just figure out at what temperature does delta G equal 0? When is this reaction at equilibrium? What do we call this on the street? Solid to liquid. Melting, we call that melting, yes, we call that melting. And so what we are trying to find is at what temperature will this sample start to melt? We're trying to find its melting point temperature, right? So to do that, we use the idea of, okay, this reaction is at equilibrium, so set delta G equal to 0. So you can rearrange that and get temperature is equal to delta H over delta S. So you just put these numbers in. Can I just do 10 over 25? Is that okay? Nope, you got to convert one of them into the right energy unit. You just need to make a match. It doesn't matter how you do it. So you can put 10,000 over 25. I think, is that 400 Kelvin? So this is 10,000 joule per mole over 25 joule mole Kelvin. And so we should get a Kelvin temperature out. So that's 400 Kelvin, all right? This thing will melt. This thing will have solid and liquid both present at the same time, only at 400 Kelvin. Because if I tell you that the melting point is 400, and let's say I heated this thing up to 410 degrees Celsius, what phase are you going to see? Solid or liquid, or both? We're above or below the melting point temperature? Above, yes, we're above it. So this reaction, delta G, actually becomes negative once we're above this temperature, because junk melts above that temperature. But what if we were at like 350 degree Kelvin or 350 Kelvin? What phase are you going to see? You're going to see the solid phase, because we're below the melting point temperature. Stuff freezes below the melting point temperature. All right? So you can, from inferencing, realize that, oh, delta G is probably positive at temperatures below 400. But we can also figure it out ourselves using the signs, all right? I want to bring it all together here, right? Delta G equals delta H minus T delta S. Usually we look at the signs of delta H and delta S to kind of figure out when is a reaction spontaneous, right? So let me just put in those signs here. I tell you that delta H is positive, and we're subtracting delta S, which is also positive. So tell me, what sign is delta G when T is small? Positive. So is this reaction spontaneous at low temperatures? It is not. So what does that mean? It means that your solid will stay a solid at temperatures below 400 Kelvin. I'm proving why stuff melts, why stuff freezes. It all has to do with delta G. Versus, okay, let's say we go to high temperatures. Okay, high temperatures. What happens to delta G at high temperatures? What's the sign? It's negative. So at high temperatures, delta G is negative. So what is this reaction spontaneous at high temperatures? Yes. So what phase should we see at high temperatures? Liquid, because the forward reaction is spontaneous. So what would the sign of delta G be then? Negative. And that's what all of this agrees with. And so when I say high versus low temperature, I mean relative to 400 Kelvin. All right, that's what I mean. All right. So that's bringing it all together. That's why stuff freezes and melts at certain temperatures. It's because we're changing the sign of delta G, either above or below. Okay. Dang, okay. All right, just two more problems. Okay, chemical kinetics. So how fast reactions go. Okay, So here's some information. If A concentration, so I have a reaction, let's just say it's like A plus B gives us C, and I like track its rate. If I tell you you combine 1 molarity of A, 1 molarity of B, you observe an overall rate of 4 molarity per second. And then let's look at the second reaction. So it looks like we're not changing anything about A, but we're doubling how much B we have, all right? So I double the amount of B that I start with, but what do we see? Do we see any change in rate? No, so what does that imply? 0, I hear 0, but it's 0 in what? 0 in B, so this implies that B has a 0th order kinetics associated with it. But we're not done, we gotta figure out what A has now. So I'll erase that experiment. Let's look and see what A is doing. So between experiments 1 and 3, it looks like A is doubling its concentration, but B is tripling its concentration. But does that matter? It does not matter because we already said that B is 0th order. So you could quadruple its concentration, it won't affect the rate at all. So really all of this rate change is coming from A. So when we look at that, the rate is changing how between the first and third experiment? Times 4. So what does that tell us about A? It is probably 2nd order. Yeah, because a doubling of A equals a 4 times rate increase. The only exponent to make that true is a 2, so 2 squared is 4. So the full rate law is rate equals K times A concentration squared. That's it. If I wanted to figure out K, I would just take these concentrations and rates and solve for what K has to be. The value of K and the unit to make that true. I wouldn't need B because B is 0th order. Okay, so let's put that all together. And how many times have you seen these 4 sets of data? A lot, yes. A lot, maybe as much as Bart Simpson. It's hoping to incorporate more of his data in our exams. Okay, which data set is consistent with this rate law? All right, so this is just applying the idea of the integrated rate law. When are straight lines important? So here we have all straight lines, just graphed a little bit differently. So we are looking for the data that's consistent with this, where A is 2nd order, and technically, even though I didn't write it, B is 0th order. All right, so we are still consuming B in this reaction. It's just not changing when it's just changing at a constant pace, because if we look at these units on the y-axis, it implies what the order is. So here for data set 1, natural log of A, that implies that A is 1st order, and B is 0th order because we have straight lines being graphed this way. So it is not data set 1. Which data set is it? 2. Here, 1 over A, this is 2nd order. And then B is 0th order. All right, so natural logs mean 1st order, 1 overs are 2nd order, just straight up is 0th order. Okay, so I think that's it. Okay, last one, Arrhenius equation. And so this has to do with, reactions going fast. So, there's actually 2 ways we can make a reaction go faster, right? Rate equals K times concentration of reactants. So to like some power, we don't know what it is. So there's 2 ways we can increase that rate. We can either increase concentrations, right? That matches our intuition. Make a reaction go faster by packing it with more reactants, more collisions. Or you can make a reaction go faster by changing K. These are different options that we can use, okay? Where changing concentrations can change your reaction rate kind of in a milder sense. You're not actually changing K, you're just changing the concentrations. Or we can change K, and that's where we follow the Arrhenius equation. That the ways we can change K, the rate constant for a reaction, follows this equation where it's related to R, the energy term of R, temperature, and activation energy. So we see that reactions go faster, or K increases, rate constant increases, if temperature is what? high. High temperatures, reactions go fast, but it's because the value of K changes, right? Or reactions can go fast if your activation energy is low. Yeah, if you just look at this, manipulate this equation, if T is big, the negative of a, yeah, if T is big, then K ends up being a, oh, you know what? I think this is backwards. That's not right. That trend doesn't work out. So sorry, I have it messed up. Where's my Arrhenius equation? Where are you? Yeah, sorry. So in your version, because yours is not editable, it's EA over RT. I thought so. I was looking at this. I'm like, wait, the trends aren't working out in my head. Sorry. EA is on the top. But it's okay. We actually never use this equation to calculate anything. Really what we get from it are trends. That as temperature goes up, K goes up. As activation goes down, rate constant goes up as well. So those are two ways we can make our reaction go faster. Both of these have to do with manipulating K, but by changing concentration, you can also change your reaction rate. All right, finally, we are done with this packet, and we have 15 minutes left. So what chapter do you want to work on? Or we can be done. I don't care. So if someone says a number from this packet, but I need to find where it is. If you tell me what to do, I'll do it. Which one? Quantum numbers. Okay, yeah. Is there one in here? 12. Okay, all right. Okay, yeah, so let's look at 26. See, yeah, I'm happy to do whatever. So the question was, let's go over quantum numbers. So the quantum numbers tell us a lot about our electron. Quantum numbers tell us what row our electron is in, you know, what period it's in. The shape of our periodic table is split up into S block, P block, D block, F block. Of where we place our electrons on our hydrogen atom. So the rules is your first quantum number is N, your principal quantum number. N can be any integer, 1, 2, 3, etc. All right, where these N values basically are the rows on our periodic table. They're basically the rows. So it's your principal quantum number, it's your shell, essentially. So N equals 1 electrons are closest to your nucleus. That's where you fill up first. You can think of like your atom like a barrel, all right? That your electrons are going to go to the deepest part first, the electrons and orbitals at the closest to the nucleus, and then you'll start building your way out. So you can think of your N levels are kind of like your, you know, shells. So this is like N equals 1, N equals 2, or you can think of them as like rows in at a concert, if you want to use my Taylor Swift analogy. So based upon the N number you are in, there's a only set number of possible L values you can have. So the rules for L are that your possible L's are all of the integers from 0 to N minus 1, where each of those L values equate to S, P, or D, or F. And there's more, but we never go past D orbitals, all right? So that means within your N equals 1 shell, the only orbital or subshell you can have is a 1s. That's it, because L is equal to 0 there. We can't have an L of 1 in an N equals 1. When N equals 2, we can have a 2s, but now we have an accessible L equals 1. We can also have a 2p. That's possible. Once we go to N equals 3, now we open up another possible subshell. We can have a 3s, a 3p, or a 3d. This is L equals 2. And so all of those follow the, you know, L can equal 0, all the integers up to N equals N minus 1. All right? And then we can keep going. That N equals 4 can go all the way out to 4f, etc. Yeah, okay, great. And then finally, M sub L I like to think of these are the boxes that you can place electrons in. So if I asked you, draw an electron diagram for a 1s subshell, you will draw just one box. So if there's one box, there's only one possible m sub L for a 1s orbital. This has a m sub L of 0. So the possible m sub L's depend on what L you're in. So your possible m sub L's are all the integers between negative L and positive L. So when you have 0, the only possible m sub L or angular quantum number is 0. Versus if I asked you to draw a 2p orbital or 2p subshell, how many boxes will you draw? 3. You'll draw 3 boxes because there's a total of 6 electrons that can fit in a subshell, a p subshell. And so this is equivalent to the -1, 0, +1 m sub L's, possible m sub L's we can have. All right. So those are the rules. And then the last one is spin, just +1 half or -1 half for an electron. So here are some sets. Tell me which ones are not allowed. Okay. So let's just go through all of them. All right. So if I have n equals 2, can I have an L equals 1? So just think to yourself, what kind of subshell is that? 2 L of 1 is a what? P. So this is a 2p orbital. Can we have that? Yes, yes. Can we have an ML of 0 in a 2p? Yes, we can, because 2p has 3 boxes. The middle one is the 0. So yeah, that's okay. And then can that electron be spin up? Yes, it can. So that's all allowed. Perfect. All right, next one. N of 2, L of 3. Is that allowed? No. If you try to write the subshell for that, that would be a, 2F. That's not allowed. All right? So here, you can't have that. The only L's that you can have for N equals 2 is 0 or 1, and that's it. So we can't have 3 or 2. All right. Next one. So 2 is not allowed. 3. Okay, N of 3, L of 2. Is that allowed? Yes. What is that subshell called? 3D? Yeah, okay. Can you have an M sub L of -2? Yes, you can. So let's just draw it out. Prove it to yourself. 3D, that subshell has how many boxes? 5. Because if you look at the D subshell, how many atoms or how many electrons can you fill? 10. 2 electrons in a box, 5 boxes. So 5 boxes. So if you do the M sub L's, you see that, okay, this is an L equals 2. So my possible M sub L's are -2, -1, 0, +1, +2. So yes, that is allowed. All right, the next one. N equals 2, L equals 2. Is that allowed? No, this is a 2D, so that one is not allowed. All right, and then the last one, this is a 2P. That one is allowed, and that M sub L is allowed. So it's just 2 and 4 are not allowed. I wish I would have made it different. I've made it wrong in the M sub L column, but I didn't because I'm not smart. Okay, all right, so hopefully that clarifies things. Those are the rules. Okay, other things. Any other questions? Okay, yeah.
Go over 6E.
Wait, which one?
6E.
6, okay, 6, but with an E. E. Okay, let's just do all the acid-base things. Yeah, okay, all right. pH. Okay, P is just a function. It just means negative log. So if I want the pH, I need to figure out what is the H plus concentration of these solutions, and we can do that. So to calculate pH for you guys, basically it's only in one of 2 camps. Either it's going to be a strong acid or base, and the calculation's pretty straightforward because we're going to make an assumption, or it's a weak acid or weak base where we have to use an ice table. So let's look at HCl. HCl is what kind of substance? It's an acid or a base? Acid. It's a strong acid or a weak acid? Strong. So we're going to make the assumption that the concentration of HCl is also the concentration of H+. Strong acids fully ionize. So this HCl gives off every single one of its H pluses, all right? So we're just gonna assume that H plus concentration is equal to 0.049 molarity, and we simply just plug that into our pH calculation. So our pH is gonna be equal to negative log 0.049, and then you should get some number, all right? The next one, sodium hydroxide, is a base. It's a strong base. So we're gonna make the same assumption, but it's gonna be a little bit different, where we're gonna assume that all of that sodium hydroxide ionizes, and that concentration is actually the hydroxide concentration at equilibrium. So we're simply going to say, oh, hydroxide concentration is equal to 0.0015 molarity. But if I negative log that number, do I calculate pH? No, this is actually POH. It's actually POH. But we're almost there. So when you do that, negative log 0.0015, you get 2.82. That's not our answer. pH is just 14 minus that. Both of these numbers will add up to 14 at 25 degrees Celsius. So the pH is actually 11.78. And that is a basic pH. Okay, great. So that's sodium hydroxide, and then calcium hydroxide. Here, this is also a strong base, but this one's a little bit special because should I just POH this same number again? Nope, you wanna do what to that number? Double it, because there are two hydroxides, so you just wanna use hydroxide is actually 0.003 molarity, and then do the same exact stuff. Those are strong acids and strong bases. They fully ionize. We just simply make an assumption that all of the H plus or OH minus go towards that pH calculation, all right? This is where these ones are a little bit different. How do you know that HA is a weak acid? Even though I told you, pretend I didn't tell you. Yes, I give you a Ka and a Kb. So I'm really trying to emphasize that this is a weak acid and weak base because I give you a chemical equilibrium constant. So we can write an ice table to help us, but thankfully these ice tables are easy because you can always make an approximation and they're always a 1-to-1 ratio. So I'll show you how to do the ice table, but it's really not that bad, right? So HA is an acid. When an acid acts like an acid, it donates a proton. So throw HA in water. When it acts like an acid, it pops off an H plus, and what you're left with is A minus. All of that is dissolved in water. So when we do our ice table, we want to put that initial concentration, 0.02, into the I line of HA. So we're going to put 0.02 right there. Okay? Like with all ice tables, we predict the change line. Which way does this reaction have to go, forward or backwards? Has to go forward because there are no products. So minus X plus X plus X. At equilibrium, we're going to have 0.02 minus X, X, X. I tell you what Ka is. It is H plus, so it's that number, but the expression is always products over reactants, so H plus A minus over HA. So let's go ahead and put those values into Ka, the E line, in terms of X. So we get X squared over 0.02 minus X equals 1 times 10 to the negative 14. This requires the quadratic formula. Do you want to do the quadratic formula? No, so what are we going to do? Approximate. So we're just going to get rid of that X. And we are allowed to do that because X is going to be really small. How do I know X is going to be really small? It's because the equilibrium constant's very small. If that's really small, there's not going to be a lot of products at equilibrium. So that denominator is going to stay 0.02. All right? Because we're just going to subtract a really small number. So now it's not a quadratic, thankfully, and then you can simply solve that. When you solve for X, X is the concentration of what? Oh, I already wrote it with my hand. It's H plus. You know it's H plus because that's what the ice table says, right? But Ka, you can think of it this way. Ka, acids make H plus. So then Kb, bases make what? OH minus. So let's do the same ice table, but you'll see that the strategy is the exact same. So yeah, that's H plus concentration, and then you get your pH right there. So are you guys good with acids and bases up there in the corner? Yeah. If you don't want to go over this, you can move. All right. Sorry, it's just distracting me as well, and I'm sure your classmates. All right, so this one, B is a base? Yes.
Sorry, will there ever be a formula that looks like the one before, so you won't ignore the S?
Oh, with a weak acid or weak base, like here? So here it is. When it comes to ice tables, yes, that the quadratic formula is oftentimes needed, but on the exam, I'm not assessing you on the quadratic formula, so it's never required that you use it to solve a question. You can always approximate to avoid using the quadratic. But here's the thing, if you do the quadratic, you will still be right. You'll still be right. But when you use an approximation, you can also be right. But if you use an approximation where you shouldn't use an approximation, then you will be wrong. Yeah, okay. Yeah, so I never require people to use the quadratic formula. Yeah, because that's not fair. Some people have fancy calculators that'll just do it automatically. So yeah, but if you use the approximation when you're not supposed to, you will be wrong. Okay. But here's the thing, with weak acids and weak bases, Ka and Kb, they're always really small numbers. So like I said, I love weak acids and weak bases because you always, like 99.9% of the time, can use the approximation. It'll always end up like this, x squared over initial concentration equals K. And we're gonna see the same thing right here, where B, when it acts as a base, bases are weird because when you put these in water, you need a water molecule also, right? Because a base is like the opposite of an acid. So this base is gonna steal an H plus from water. And when it does that, it becomes Hb plus. But when that base steals an H plus from water, what's left behind in water? If water loses an H plus, now you have what left over? OH minus, be very careful of that sign. So do you see why B is a base? Yeah, because it makes hydroxide on the product side, all right? So here, we're gonna do the same ice table and we're gonna get the exact same result, all right? But I'll do it anyway. So here's our ice table. You put a 0.2 amount of base in. I don't really care about water because it's a liquid and it's not in the K expression, all right? And so the change line here, this reaction has to go forward, so minus X plus X plus X. Again, I'm ignoring water because it's a liquid. So at equilibrium, you have 0.02 minus X of the base, X of this Hb plus thing, and then X amount of hydroxide. So when you write out the Kb expression, products over reactants, what's it gonna look like? X squared over 0.02 minus X. Does that look familiar? Yes, it does. Equals that Kb that was given, 10 times 10 to the negative, or whatever, -5. Do you wanna do the quadratic? No. So we're gonna just approximate and get rid of that minus X. So this doesn't require the quadratic anymore, it's just normal math. So when you solve for X, it's the concentration of what? OH minus, how do you know that? From the ice table. That's what X is in the ice table. Or you just memorize it this way. In the Kb expression, X is hydroxide. In the Ka expression, X is H plus. And it ends up being the same. It's X squared over initial concentration equals K. Yes?
Is the K guy supposed to be 1 times 10 to the 14?
It's not 10 to the 14. Oh, no, yeah. No, it's what was given. It was what was given, yeah. Okay, there we go. And that's it. Is it that bad? X squared over initial concentration equals K. X is different depending on if it's you're working with Ka, an acid, or Kb, a base. That's it. Okay. All right, 5 more minutes. Last ditch questions. Yes? Yeah?
Oh, okay. So like if you have a larger electronegativity difference, that means it's fourfold.
That the bond, yeah, so the question is if delta En is large, yes, typically that means the bond dipole is also large. So here's an example, like CH, that bond has a very small electronegativity difference. So its bond dipole is basically nothing, right? Versus if I have a CO bond, if you actually had numbers and calculated delta En between those two atoms, right, like actually use those numbers, you'll get a really large value. And when you do that, you'll get that you have like a huge bond dipole. Yeah, yeah. So for example, if you wanted to, if you drew this, if I had C, I don't know if this quite works out. Okay, we'll do Cl. All right, and then Br. So both of these compounds are polar because you can tell, because I have one polar bond. I have a CCl bond and a CBr bond. They're both polar. That they're tetrahedral, that, unsymmetric makes it polar. But one of them's more polar than the other, and we can probably predict it based upon electronegativities. Here, your delta En difference is going to be large because chlorine is part of the high five, but bromine is not. So here, you're going to have a larger bond dipole. You'll still have a bond dipole over here, it's just going to be smaller. So I predict if you looked up polarities of these solvents, you'll see that CH3Cl is going to be more polar, probably. Or it's going to have more polar properties because it has a larger difference in electronegativity. Yeah. Yes. Yes. Yes, the format is the exact same. The only difference is that there is an hour and 45 minutes, so 105 minutes. I added 5 more questions. So your final should, if you just scale it exactly, you should have 45 questions on this exam, but I actually put 50 on there. And you might be like, oh, that's so mean, but no, I added 5 easy questions. All right, 5 easy questions to kind of give you more opportunities to earn points, right? Because if you get one question wrong on a 45 question assignment, it's worth more than if it's a 50 question assignment. Yeah. Oh, it was real low. It was real low. It was like I don't want to share it. I don't want to share it. What? No, I don't want to share. There's only 50 people in the class, so it's harder to gauge. Yeah. Oh, so there was a question on here, the lab final, about adding an inert gas such as helium to an equilibrium reaction. So here, so this is Le Chatelier's principle. All right. So if I add A to this reaction, so this reaction's at equilibrium, if I add A, how does it shift? Adding A pushes the reaction forward. If I add B, it pushes it in reverse. If I squeeze on the reaction, it's going to move towards A to like relieve, make less moles of that gas, because squeezing it increases the pressure momentarily. So the question here is, well, what if we add helium to this mixture? Will it change the chemical equilibrium? So I ask you this, is helium part of the equilibrium? Is it in K? No, it's not. So the whole idea of Le Chatelier's principle is that when you change concentrations, when you make a disruption, you're changing K into Q for a moment. So if you add helium, there's actually no change in chemical equilibrium because helium is not in the equilibrium constant. Will that answer the question? So you'd think, yeah, adding helium increases the total pressure of your system, but the partial pressures of A and partial pressures of B don't change. You're just adding a new contribution, changing the total pressure. Okay, can you explain the ice tables again? No, you can look at the recording. What was last year's average? Can't say it. Which packet is this? This is the one on the, I don't know, we just started talking about random stuff, so it's not on any packet. Okay, all right. So go forth, best of luck. I will post this like in an hour and a half. Good luck, everybody.